Yeah. So welcome to this Flange calculation workshop organized within the Plant Engineering Workshop 2020 by INIPED. It is my pleasure to introduce you to Mr. Watermans. He's a Redback director and as well as INIPED director. So he will give us a wonderful workshop, hands-on workshop with some calculations about Flange calculation. Rutger, it's all yours. Thank you.
Okay, thank you, Javier. Hello, everybody. I hope you can hear me well, and if not, just let Javier know, and we will try to do something about it. In this presentation, I would like to tell you a lot of different items about the calculation. On one hand, the EN 5091-1. But also about the flanges, the mechanics of the flanges, including the behavior of gaskets. This is actually an introduction for a training we normally give for the EN 5091-1 because it is quite a complicated calculation, and especially the interpretation is rather difficult. As Javier told you, that Redback is a company which works together with INIPED and brings all his training to INIPED. Redback is a collection of engineers, consultants, and we have some software products for doing the calculations. And the cooperation is already some years, and that's working very well. Let me see how to change the screen. We are going to talk about bolted flange. With bolted flanges, we have what we call opportunities. Some people say there are problems, but we see them as opportunities as well, safety-wise, as environmental-wise, and also for maintenance and operation. What you see here is the bottom of a flange of a large storage tower or storage tank, and this is what happened after so many years. This flange, although well painted, started leaking after a while, and you can see from the facing that something is wrong here, and the whole system is not very leak tight. So this is not an old flange, but this is what happens with flanges. For some of them, after a while, they are in operation. Redback is a company who specializes especially on difficult items, problems, damages, corrosion, erosion, difficult connections which are outside the scope of calculation codes. In this case, you're looking at a aluminium storage tank for, I think it was milk. Unfortunately, with the calculation of the bottom cap of this vessel, they forgot the static head of the water and during testing, and of course also the milk later on, and it started buggling. They wanted to know, is there something we can do? And we did the engineering for them. And we said, well, there's something you can do if you can repair it, because it is very thin wall aluminium, and you can bring it back in its original shape. Then we present you the solution. In this case, the solution was to reinforce around the knuckle and making it stronger against buckling. Redback is cooperating with different companies. They are listed over here, where we have at the left top Dijkgraaf Support. We have ITIS, Progresso, INIPED, Bailuna, and Wenzel Dynamics. And sometimes we also work with other companies as partners to solve specific problems. Each of these companies have their own specialism. For instance, Dijkgraaf Support is very good in flange integrity management, training flange operators, flange mechanics, how to handle flanges, the bolts, and what different tools you have around bolting. It is a industrial testing and services company. Wenzel Dynamics is a real calculation for finite element analysis. Redback are the engineers and consultants with some software products. Inipet, the training institute. And with the training institute, there is the advantage that a lot of trainers are specialists themselves, and we can communicate with them if there are different issues to be solved. Here is a list of websites which you can visit to get more information. The important thing about flanges is that you get a good feel how flanges work. It is a combination of components, the bolt, the flange, the gasket in between, and also the connecting piping or shell to the flange, and hopefully in most cases also the washers which protect the nut against any additional friction it would have otherwise directly with the flange. And it is very important to understand how this works together. And I will explain a bit more about the flanges. The intention of a flange connection is to make sure that it is the same integrity, the same leak tightness as a weld. They are both in the same system, but they are not treated that way. Weld connections, you have welders which are classified, they have certain certification, the procedures are well established, and also the testing, non-destructive testing is well defined. For flange connection, it is not always the case, but in some cases it is more like anybody who can hold a tool in his hand is allowed to make a flange connection and bolt it together without too much knowledge about how the flange itself is working, and that's a bit strange. I have a question to you, and you think about it. We'll give later on. I will give the answer. The question is here. I'm not sure whether this screen is always on top here, but move a bit to the side. The question is as follows. You have assembled a flange connection, for example, with piping, and you're going to test the assembly and see whether it is holding the test pressure. And the question to you is, does the bolt force due to this internal pressure, test pressure, does it go up, down, or stay the same? So I get always different answers to this question. One seems to be plausible, but the other one is actually the reality, and I will tell you later on what is the correct answer to this question, because that is very important to understand how the flange work. Flange calculations with the SME and also currently in the EN, I think it is clause 11, the EN 13453 is based on the Taylor Forge method. The Taylor Forge method is relatively old, from the 1930s, and it was considering the strength of the flange mostly, and was established to make sure that with the bolting there was nothing broken, not the bolts or not the flange itself. In the old days, the bolts were not that strong, The flanges could hold more, but later on they found out that as these bolts got better and better, these materials, the flanges sometimes were overstressed, and the Taylor force made sure that that was not the case. It considers the stresses in the bolt, it considers some stresses in the gasket, and it considers the stresses in the flange. There are different type of flanges, which are also handled by the Taylor forge method. In the middle top picture, you see the integral flange. Integral means that the hub and the flange ring, they are one system. At the right, you see a loose ring flange or a loose flange. And there are all other types, blind or blank flanges, or even equipment flanges, which are sometimes a combination of these types, which I just mentioned. The connecting shell, meaning or the pipe to a piping flange, or the body shell of a piece of equipment, has an influence on how the flange ring behaves and whether it is in addition to the strength of the flange or not. The basic approach of the Taylor forge method is that it considers of course, the bolt force itself, as shown at the right. In blue, the gasket pressure, which is a result of the bolt force, but also the fluid pressure inside the pipe and shell, and sometimes also acting for a small fraction on the flange itself, just next to the gasket, the blue part in the picture here to the right. And you can see at the left that the fluid pressure, the gasket pressure, they more or less add up to the bolt force. And I can tell you that is not entirely true, because there are also other influences. Here you see a bit in 3D the different vectors. The W, which is the bolt force, the HG in the middle, in the brown section of the gasket force, HT, some of the fluid which is on the inside, and the HD is also the fluid pressure, which acts actually on the small part of the hub in this case. The S.
Excuse me, Rutger. If you want to use the mouse, hover the mouse where to point where you are. Yeah, that can help a bit. Yes,
okay, it shows. Okay.
You can see your mouse. You can also get the laser pointer, which is better. The laser pointer. If you want to try to get it from the toolbar on your left, but then the mouse is okay. The mouse is fine.
Mouse is fine. I will use the mouse.
Yeah.
Okay.
Thank you.
Thanks. To repeat the W force here, which is the bolt force on this side, connecting the flanges. Here we see the HG, which is the pressure force of the gasket, a resulting force. The H2, which is the small force. In this case, it is not really visible because there is no part of the gasket subject to the fluid pressure, but in this inside ring, it will be. And the whole section here, which is the internal pressure, results in the HD, which is the force which pushes the flanges from each other. All these forces, they have lever arms, and they are connected together via this is flange, and they result in stresses around this hub connection, and they are defined as the stress in radial direction. This is the SR, the ST, the tangential stress, and the SH in the horizontal section, the stress. These are calculated within the Taylor forge, and when these stresses, which are resulting from all the other WH pressure forces, if they are within limits, then the Taylor forge says, okay, this flange is acceptable for the calculation. Here again, it is a bit summarized with regard to the bolt force, the fluid pressure force. Some of the lever arms are indicated over here, and again, these arrows are also indicated over here. This is the ESME or the Taylor forge calculation sequence. Load condition and bolt are calculated, then the load on the flange, lever arms based on the dimensions of the flange and the gasket. There are some factors which need to be included. That depends, for example, what type of gasket you are using. And then the stress in the flanges is calculated, as I shown you in the previous slide. I will not go into detail here because that's not the method of this presentation. The Taylor forge method has its limitation because with regard to leak tightness, okay, stresses in flange, bolt and gaskets are reasonably well calculated, but how about the gasket stress? Is it overstressed or is it under stressed? Do I have too little stress on the gasket to provide a good leak tightness? And therefore, it doesn't tell you anything about the leak tightness of the whole assembly and the gasket in particular. And that's something why you make this calculation also to know something about, of course, the leak tightness, which is not handled in Taylor forge. And it was originally also not designed to have that as a focus. A bit more about the Taylor forge method. Actually, there is there are two factors, the M factor and the Y factor. In this case, the M factor is a gasket factor, which tells you that if you have this absolute pressure, which is the P, times the M, you require a gasket compression stress of Q as a minimum to get a good connection, and that's all. As I stated here, this approach does not treat all load conditions. For example, with regard to assembly and operating, they are handled, but the assembly, the test, and all other service conditions, for example, when you start up a plant, it will go through different steps of pressure and temperature conditions, which you need to take into account in some cases to get a proper leak tightness of the flange assembly. The EN 1591 is a different calculation method, and is a European calculation method, and therefore it falls under the legislation. A few things about calculation and legislation in Europe. The EU has a so-called CE marking, which has a general idea about safety and about equality within the European market. Within that legislation, the Pressure Equipment Directive was defined, dealing with pressure equipment, as it says over here. Also, the pressure calculation code falls under this PED, this regulation. And of course, the EN 5091 falls under this legislation. Therefore, it is law. This calculation method has also the intention to do something about the environment. And we know in Europe some of these directives, like integrated pollution and industrial emission directives, which this code addresses, together with this EN 3555, which is dealing with gasket parameters. So as I told you, that this the approach is dealing with the safety and the environment. Environment in the sense that it will give you a leak tightness. I have to watch the time because there's much to tell about this subject. The EN 5091 was a calculation method which originates from the German Democratic Republic, which was Eastern Germany, and it had a different approach. And not getting in too much of the details, a gentleman, Mr. Wilful, he passed away, unfortunately, beginning this year. He was relatively at a good age. He adopted it for the EN code, which further developed in this EN 5091-1. The -1, the part 1, concerns about design rules for circular flange connections. The part 3 is a metal-to-metal approach. There are other parts which I will not discuss at this moment. The CR 36443 gives the background information about the rules and what the theoretical mathematics are. The flange calculation is relatively new for this the industry. The verification is currently done by seeing what is happening in the field actually, and the results are promising. There have been already problematic flange connections for which calculations have been done with this calculation method, and the results were promising, and it's going to be applied more and more. These are more, this is more information about the parts of the EN 5091. The calculation part, as I said, gasket parameters, and also defining the tests for the gaskets. The metal-to-metal flanges, and part 4 is comparable with the ESME PCC1, which tells or gives work guides, information, procedures for competency testing and training for flange mechanics, so that they indeed take care of handling the gaskets correctly, preparing bolts correctly, using correct bolt torque tools, and so on. This is in 3 sheets actually the procedure how the EN 5091-1 addresses the calculation. I will run very quickly through the overall procedure. The numbers here, 1 to 50, is the number of formulas almost that are being used in the calculation. There are many formulas. In these first part, in this first part of the calculation, parameters, dimensional parameters are being calculated to set up lever arms, distances between force, surface areas of the gasket, and so on. Then in the calculation, there is an assumed gasket force. One would say, well, you take a bolt force here. No, the calculation starts off with an estimated gasket force to start the calculation, because the whole calculation is an iteration process to get the minimum bolt force required for the leak tightness you have defined in the beginning. With that gasket force, you will start the calculation getting into the behavior of the gasket to get the correct width of sealing and the surface area of the gasket. Then you try to get and change this assumed gasket force and to see whether the gasket width changes up or down. After a while, after some iterations, you will get a gasket force for which the gasket width remains constant within the leak tightness limits you have set before. If the gasket width, which is not the complete gasket width in some cases it is, but in some cases it isn't. If the gasket width is constant, you will go to the next part. Now you know exactly in this part of the gasket where the correct lever arm is. That's the distance from which, for example, the bolt force works to rotate this ring, for example, but also the other forces, the internal pressure forces, how it behaves and what is the rotation point. But then you have only, after this calculation, the gasket flexibility in new lever arms. After that calculation, you have only the assembly condition. Now you're going to check with the other load conditions, and you will take into account the pressure and also the temperature. And because of the temperature, for example, the bolt will, due to thermal expansion, will get some elongation, but also the flange, also the gasket, everything will move a little bit during the subsequent load conditions. You will do the calculation and check whether for all these load conditions you have a correct result and the leak tightness remains correct. And that is also an iteration. And if the required force is equal, your starting gasket force is equal or even perhaps larger, you continue. But if the required force is not equal or is lower, so you do not have a leak tightness during the subsequent load conditions, you will have to go back in this process, and you have to change the calculation and increase the assembly gasket force. If that iteration, so that is the almost the outside iteration, is okay, you continue to the next part. You will do the calculation for the bolt load itself. With all the lever arms, you can calculate the bolt load. You will calculate bolt scatter. That means that if you tighten the bolt, there is a margin when you use, for example, a torque wrench for the plus and minus of this bolt force, you will not ever exactly address that particular bolt force. And to take care of that scatter, you will calculate the minimum of that scatter. You calculate the further load limits. With that bolt load, you will get into the stresses of the flange, the bolt, and the gasket. And if these stresses are okay, and they are within limits, then the design is acceptable. If these stresses are not okay, and because of the gasket, you need a much higher bolt force than is actually possible with the combination of the flange and the bolt, you have to change the design and start all over again. So that is the whole loop of the calculation method. At this point, I would like to show you a bit in some calculation what I mean. Let me see, go back. With this width calculation. How can I go back? Oh, this is better. Sorry for my a little bit difficulty on this computer. This is relatively small probably on your screen, but this is an application we use for the EN5091 calculations. At the left, you see different flanges. I can browse through them and you see the different types over here. And so this is a blind flange with a bolt set. This is, for example, a loose flange. Here we have a regular piping flange and so on. The nice thing of this application is that it draws immediately what you have designed yourself. So you can see whether when you make a design mistake. And since there are many dimensions to be entered in this application, it is very nice to have a good verification of these dimensions by use of a graphical impression. In the middle of the application, you can enter all sorts of data. This is some information about the flange. Here you see some dimensional values and some detail values. You can also see that it will show you some overall dimensions of the flange you have selected. Here you see about the gasket. This is a spiral wound gasket. It has an outer ring and an inner ring of metal, and the sealing part is in the middle here. I will not get into detail of all of this, but also the bolt is drawn with the washers. You get a good feel of the size of the bolt. The connecting shells are drawn here, and you give the different load cases. And with these different load cases, you have the assembly load case, which is at 20 degrees ambient temperature, the test case, and then the different operation cases, which you can see over here. The allowable stresses are indicated for the different load cases. And we can do a calculation. And we can do a calculation as a summary report, a detailed report, and some formula-based iteration. You can see the information which I will show you. The summary report is very quickly an overview. If you're familiar with the software and you know what you're looking for, you get an overview of these different conditions. At the top, you see some information of the flanges, the material, here the bolt material, for example. The load conditions are shown over here. And below here are some values. I hope you can read this a bit. I will Control A, copy, make it for one time a bit bigger. Here. Here it is a bit bigger, these values. And unfortunately, the symbol here is not correct, but this is a C. If these values are below 1, it means that the component as such, in this case, for this first line here, is below 100%. So 1 is loaded for 100%. So in this case, if we look at the bolt load here, is only 60 or 46% we use of the allowable stress of this bolt during assembly, because that's the assembly conditions. And here you have the different load conditions. But what I wanted to show you is very quickly, you have a detail report with more information, sometimes necessary for notified bodies. You get all sorts of intermediate results. And within the software, you can also see at formula base per formula, and this is quite long report, which I will not show you. But we will look, I wanted to show you about the gasket width. I have to look here. I can only look at one formula. Last iteration, all the iterations. Okay. And here you see from all these formulas one iteration. And what do we see over here? This is actually the calculated gasket width. And 1 second here. In some cases, due to rotation of the gasket, the width of the gasket used for sealing is smaller than the overall gasket width. However, here it remains continuously through these iterations the same. And that is something what frequently happens when you use a spiral wound gasket, because the gasket width is already limited. If we go, for example, to a different setup, number 13, this, look a bit. Here you have a long gasket with a relatively flexible European low pressure gasket. And of course, due to this bolt force, this flange will rotate somewhere around this particular point here. And you get the phenomena which is shown over here. If I do the same calculation, 53, I think. And now you see something completely different. For example, if we take these numbers, and I hope you can see something of it, the starting point was 51, which is the overall width of the gasket here between the end and the raised face. It reduces to 12, and it goes up to 8.5. So only a small portion of this gasket is used for sealing. And this is what I wanted to show you in the gasket calculation. And you can do numerous evaluations with a software code like this, a software application like this. I will go back to the presentation. So we have seen that phenomena, which was part of the first iteration sequence of the calculation, from which then is decided how much gasket stress is necessary for leak tightness, and then that is back calculated in the necessary bolt load and stresses within the whole flange assembly. I get some questions. I have a few other things to show, which I will do very quickly, and hopefully I will be able to answer those later on. Bolt tensioning is something to take into account, depending on the friction between the nut and the thread of the bolt itself. Whether you use any grease material, whether you have clean surfaces, and also the nut turn on top of the flange, which we do not advise. We always say use hardened washers in between, because otherwise you lose a lot of torque in the friction. All this stuff you need to understand and take into account when you design and calculate, or you assess a flange assembly in the field. Another thing, these are all aspects which makes the flange connection and assembly somewhat difficult, but also a nice opportunity to investigate. For example, if you're dealing with large flanges around the tube sheet, for example, of a shell and tube heat exchanger, you get into this type of issues. For example, with temperature, within the calculation code, I didn't show you, but that's possible. You can use different temperatures for the bolt, for the flange, for the shell. Oh, I'm going one to go one back. Can I go one back? Yeah. As is shown over here, this is from a report, and we made a nice drawing of it, where you can see that there is a temperature of 260, but the purple line is actually the temperature of the bolt in different parts of the bolt. You can see that these temperatures can be different. What you can do in that case is, for example, when the flange is not insulated, the bolt is open to the air and will cool down here, that you will reduce the temperature in the bolt to simulate the temperature, the overall temperature of the bolt in the calculation. There's another phenomena around flanges, which we also take into account in the calculation, which is not so much part of the EN 5091, but it is a well-known fact that at high temperatures, the bolt will have some sort of stress relaxation, meaning that the material will set at these high temperatures, and you can see that we are talking here 300 to 700 degrees, that if the flange is in operation, after a while at high temperature, the bolt will lose some of its original bolt load. And what you see is that during maintenance, sometimes these bolts are retorqued to the original bolt torque and bolt load to make sure that they still have the same bolt load as was originally intended. Bolt relaxation is a difficult issue because this is only after 1,000 hours, and these tests, they're only, I think the British standard has some information about the bolt relaxation. This is a phenomena to consider if you're dealing with this type of bolt material in the high temperatures. Bolt forces. You can calculate anything on a bolt and on flanges, but if the forces due to thermal expansion, due to other things, if you add that to the flange, you can get into situations like this, that the flange will rotate in a strange way, and you might get leakage. So first of all, include additional forces and moments in your calculation, which is possible in the EN 1591, to make sure that you can take care of some forces and moments. But on the other hand, also inform your pipe stress engineer that he does not overstress flange connections. A little bit about gaskets. Gaskets are being tested, and the standard for that was the EN 30555, and these are leak tightness tests. And this is the machine to do the leak tightness test. It's all defined within the EN 30555, and these test values are being used in the calculation. And in short, what is happening is that in the vertical direction, the gasket stress, so it is started to stress, and then they release the stress again to a certain point and see how quickly in the x-axis how much it comes back to its original shape. And the x is actually the gasket deflection, and the gasket deflection you can consider as reduction in thickness. So that means if you started off with a 4mm gasket, after continuous pressing, it will only come back to 3mm, for example. These items are being tested in the test procedures of the 13555. This graph indicates one of the results, which is taken into account in the calculation, that the thick line is actually the pressurization of the gasket, and when it is in operation and release, it will go along the thinner lines back, and in the vertical direction you see the leak tightness. The lower you are here, the more leak tight it is. So if you want to, for instance, to this point where I'm pointing at the moment, that particular leak tightness, you will have to pressurize it all the way up to here to stay within operation and keeping it to this leak tightness over here. This is a profession almost on its own, gaskets and the leak tightness of gaskets, which we will we discuss normally during our course about the EN 1591. This is a flange model in which actually all the mechanics of the flange have been symbolized. In this case, you see, for example, the elasticity of the bolt. This spring is actually the elasticity of the gasket. You have within the hub this elasticity, and actually this is the moment around this point within the gasket hub. Also, the internal pressure will push out the different parts of the gasket. And let me see, is my computer empty? 1 second. Yeah, one moment. I'm working on a laptop at the moment, and it has a battery. And, yeah. This particular model gives actually how the different parts move within the flange model. I can see that we are almost an hour within this presentation. I would like to leave it with this. Let me see, and answer some questions we have. I can browse quickly through these documents, and here are some examples, but that would be then for a later case. The question I said about will the bolt force go up or down during test conditions, actually the bolt force will go down. And you can see it a bit illustrated within this graph, that due to this arrow becoming less, and it's actually part of a moment, it will lift on this side and the bolt force will go down. This needs some more explanation, but you have to believe me, this works this way. I would like to leave it here and see whether we can answer some questions. I do not know how that works, Javier, to see the questions.
Yeah, thank you, Rutger. I saw a bit later a message in the chat window from Antonio Tony Martinez. I don't know if you have already mentioned that he was giving his answer to this question.
Yeah.
I don't know if you can read it yourself.
Let me see. Okay, yeah, I can now open the window, I think, with the chat.
Yeah.
And what about my opinion? The answer to the question is the bolt force not change. The tightness force should maintain equal. It can be some relaxation of the force after the test. So this is an answer I frequently see, but that's not entirely true. As I explained just now, is that the bolt force will go slightly down. It depends how much down it will go. It is not so much. It is not that it will leak immediately. But most people answer this question. They think, okay, it's under pressure, so the flanges will be moving apart, so the bolt force will go up. But that's not the case. It will rotate along the gasket because it is a how do you call a equation of moments rather than only actual forces.
Thank you, Rutger. I think we can leave some time for participants to send their questions via the chat, or just since we are not so many people, you can just unmute your microphone and go ahead and make the question with your microphone.
I see one question from Jai. What will be the gasket stress when the width decreases? Of course, if the flange rotates and the gasket stress width decreases, the gasket stress will go up. And the funny thing is, in most cases, people think that the SP flanges are stronger than the European or German flanges, which is true. However, for flat gaskets, that is beneficial for the leak tightness. You need less bolt force to rotate the flange, decrease the width of the gasket, and you have a quicker leak tightness than with the stronger flanges. So the SB flanges are indeed stronger, but for the leak tightness, that's not always an advantage.
Thank you, Roger. You get a question from MG.
Yeah.
You can.
Mr. or Mrs. MG, is there any difference between the calculation methods proposed in the EN 5091 and the EN 3453 Annex G? The source of both calculations are more or less the same. However, Annex G has simplified a few items around the gasket and uses general gasket properties and not measured properties. However, the mechanics of calculating the flexibility, the elasticity of the flange has the same background. So that is therefore also completely different from Taylor force. So there is difference. So the 5091 is more detailed and further advanced. And I think that the Annex G and the Annex GA will probably be removed in the future. I'm not sure. Those are two different committees, so everybody has his opinion. I see another question of Punjai Pankai Kumar. Do we have experimental data on gasket from most of the manufacturers, or are we still using M values from ASME? I can show you that there are many well-known gasket companies having tested. I think we have around 500 different types. There are not 500 gasket manufacturers, but different gasket types have been tested right now, and they are available on. I will in the chat give you the internet address and gasketdata.org. That's where the material properties are published. Again, a question. For RTG type gaskets, will the same principle apply or any other additional parameter approach need to be followed? No. The EN 5091 takes into account RTG type gaskets, so you can calculate the same for RTG type gaskets. However, the experience with RTG type gaskets is that don't use them when the temperature changes a lot. Use them when they are in a good, I would almost say, laboratory type of environment. Because when something is not correct, for example, the facing is not completely clean, or there's some misalignment, or there are temperature differences, you understand that this solid RTG ring type joint will not be very flexible to such changes in conditions. I get a question saying thanks a lot. I would say you're welcome, and feel free to send any questions to Inipet, to myself, based on this presentation. And
yeah, thank you, Rutger. As you know, as the participants know, you can send questions via the Telegram bot application or also the website that you have received a personal link to get in touch with the speakers. So I encourage you to send questions, and because that will increase the discussion as well.
Yeah, indeed. I see one question here. So what about bolt changing? Does this allow such calculation? Yes. Whether you use a bolt, the size of the bolt, of course, the material of the bolt, the number of bolts, whether you have a shank in the middle of the bolt, so it is less diameter in the middle. All these things are taken into account in this calculation. So I think we can leave it here. And I thank everybody for joining, and Javier for hosting this nice meeting. Thank you.
Thank you very much, Rutger. It was very interesting, and we hope the discussion will go on during this plant engineering workshop week. Okay, thank you very much, and everybody for attending. And we will stop the recording now, and we'll close the meeting. Thank you very much.